let's talk isothermal transformation diagrams. So these are a little tricky, but there's a couple rules to follow, right? On the bottom, we're gonna have time in log. So 1 second, 10 second, 1,000, 100, 1,000, 10,000, and on, right? So it's not linear. It's not 1, 2, 3, 1, 10, 100. On the other axis, we have the temperature. So what we're looking for here is the microstructure we get at a given rate of change of temperature, right? So we're gonna follow the temperature down. So we start at 1400 and it cools it down in 1 second, right? So we draw a line from right here to right here, right? The line in this can only go down or right, okay? So think about it this way. The line, when something's cooling, it can't go back up. It can only go down. It can only go this way or slightly, or straight down with a slight tilt over to the time, because we can't go back in time or stay still in time. This curve is going to tell us what microstructure we get. So if the line crosses through this area, so it goes straight down, we're going to get martensite, which is a very hard, brittle steel, which could be what we want. If it goes through here, this B region, so it cools down, stops cooling down, and goes straight through, we get what's called bainite, which is less brittle than martensite, but still pretty strong. If the line starts here and just goes straight through this FP region, this is known as fine pearlite. This is what a lot of steels are. It's just a general purpose structure that's pretty ductile, not too brittle, not as strong as it can be, but still pretty useful. If it cools down like crazy slow, we'll get what's known as coarse pearlite, which is has very, very large grains, so it's very ductile, but also very weak compared to what it could be. So the first line here is when we begin the transformation. There's actually a line that goes through the middle that's known as the 50% line. And then here is when the transformation has ended. So if we have a steel and we want it to be as hard as possible, so it's going to be a chisel or something, we're going to cool it down in 1 second, right? So that's the line, crosses through the martensite region. That's going to be 100% martensite. If we want bainite, we're going to have to cool from 1400 to 600 in a little over a second, and then hold that temperature for a couple minutes, and then it can go back down. If we want a coarse structure, we just have to hold the temperature and let it cool down slowly. So it's all in the rate of cooling as to exactly what material you get. Now, every composition of steel has a different isothermal transformation diagram. So some steels will have no gap right here. So if the isothermal transformation diagram looks like this, we can't get martensite because the line has to go down. It'll go through that fine pearlite region. That's the only structure we can get. So that is typical of a lower carbon steel, so maybe a 1020 steel. As you raise the carbon in the steel, this, what's called the pearlite nose, will move to the right. So why does that matter? If we compare 3 different diagrams, low carbon, we have no area to go from here through here without passing through the beginning and the end of the transformation. For something with a medium carbon amount, we have a clear line to clear this pearlite nose and start the martensite transformation. But say we only have one second to do that. If it's a large part, we can't cool down something that weighs 50 pounds in 1 second. If it's like a knife blade for a pocket knife, sure. But something heavier, like a large casting or something, we couldn't do it. So one of the reasons we have alloys is to make things more heat treatable. And this shows up in the chart over here. So with a high carbon or a high alloy steel, they're designed so that there's more area right here, so that you can start up here and the line can have an easier slope. So maybe you give yourself 10 seconds to cool that part down to make that full transformation to a martensite, a hardened steel. So this is one of the things we look into when we talk about a steel's heat treatability. If you have a shaft that's 6 inches in diameter, it's not good enough if only the outside inch has been heat treated, because the inside can't get rid of the heat. So things like chromoly steels, if you look up the isothermal transformation diagram, you'll see the nose is pushed way to the right. It just gives you more time to achieve that drop in temperature, to achieve the desired microstructures.